Hi, everyone. Thank you again for joining. And here we are for our second session of the day in this meeting room. So with us, a really pleasure to have Grace Jansen. Hi, Grace. How are you?
Hi, good, thank you. How are you?
I'm okay. Thank you so much for joining us. And we're also going to have Kate Stanley. She's having some issues connecting, but hopefully we're able to fix that out really soon and she'll join us. So today, Grace and Kate are going to present reacting to an event-driven world. So thank you so much for bringing these to us today, and I'm really looking forward to see your presentation. So without further delay, please, Grace, feel free to start.
Absolutely. Thanks for having us. So, as Roberto said, unfortunately, Kate is having some technical difficulties. So hopefully she'll join us as soon as she's able to via Zoom. But for just now, I'm going to get started and kick off with our presentation. So thanks for joining us. This is Reacting to an Event-Driven World. I'm Grace Jansen, and Kate will be joining, and we both work at IBM. So we're going to talk about sort of the fact that data and sort of the huge quantity of data is almost exponentially growing. The values on this graph don't necessarily matter. It's just to sort of prove the point of, we've got this exponential curve, and our applications nowadays are having to deal with absolutely ginormous quantities of data. And it's just not just the quantity that our applications are having to deal with, it's also the fact that, there's this fluctuating load, and we're not sure about, on Black Friday, for example, we might have a huge spike in number of viewers of traffic going to our websites, to our applications, compared to a normal day, a sunny weekend in the summer, for example. So how can we architect and design and build our applications to be better at dealing with these fluctuating loads and this ginormous quantity of data that we're now generating? And it's not just that. Customers now have an increased expectations of their use of applications. When they're using these applications, they're expecting, real-time app updates based on the data available. They're expecting these applications to be responsive to whatever commands or clicks or sensors they're giving them. And they're expecting to have real-time intelligence based on that. So our apps have to be able to react as soon as possible to events in real time. Our apps have to be able to deliver responsive customer experiences, and our apps have to have real-time intelligence built in. So how can we design all of this? Well, let's take a look at how systems were designed and how things like event-driven architecture can help with that. So, time to get some coffee, because every presentation needs a coffee demo. I think it's compulsory nowadays. So there are lots of different demonstrations out there that look at things like event-driven architecture and when and how it's a good replacement for things like traditional communication like HTTP. So we're looking here at one by Clément Escoffier from Red Hat. It's a really good example. It's a coffee shop demo. If you want to take a look at the code, here is the GitHub repo for you to take a look at. So in this example, we have our coffee lovers. And our coffee lovers communicate with a coffee shop via HTTP requests to give their coffee orders. And then in the original example and the original application, it would have been HTTP to the barista to give that coffee order to the barista to make. And then the barista would then send HTTP back to then tell the coffee lovers, your coffee is ready. Now, the issue with this is this might be fine if it's just me going into the coffee shop and I'm the only one asking for coffee and I'm not in any rush or anything. I'm sure I'd be fine to wait at the counter until my coffee is done. But if everyone listening to this webinar came into the same coffee shop, let's say we've got like over 300 people coming in to get coffee, well, we'd have a huge queue at the coffee table, and we'd all be wasting time waiting for the barista to essentially make our coffee and then give it back to us. And the barista can only work on one coffee at a time with this. So how can we architect this better so that we can make more efficient use of our time, more efficient use of the resources available to us, so the baristas, and essentially make a more responsive and a more asynchronous system for our coffee shop? So alternatively, the HTTP between the coffee lovers and the coffee shop is actually fine. We don't necessarily need to change that. Reactive isn't necessarily needed. Reactive messaging isn't necessarily needed every single time. So we've left HTTP there for just now. But this time, instead of a HTTP call to our barista to tell them the coffee orders, instead we're going to add in this event backbone. So all of our orders are going to go into a queue in this event backbone in order of when they were placed. And then that backbone can be read by the baristas. So as the baristas are making their coffee, they can essentially see sort of which order is next in the queue. They can also look at, they can also make multiple coffees whilst looking at the backbone. So they can go off and make a cappuccino, and whilst that's brewing, they can then come back to the event backbone, check the next order in the list, and start making that. What this also means is that you essentially you can have something called a board. So instead of me having to wait and continuously ask the barista, is my coffee done? Is my coffee done yet? Now I can go away, leave the barista bar and sit down with my friends, talk about Java, as we all love to do, and just wait until an update on the board tells me my coffee is done, and then I can go up and collect it. So this way, I'm able to use my time more efficiently whilst I'm waiting for my coffee. I don't have to stand at the counter waiting for it and not be able to relax and take a seat with my friends and chat. And the barista is able to work on multiple coffee orders at once. So it's a much more efficient system. And this is how event systems can really help in making it more asynchronous, more reactive, more responsive to the users using it.
Okay, so sorry, Grace. I think we have Kate with us now. Hello, Kate.
Amazing.
Can you hear us? And we can see you at least.
I can hear you. Can you hear me?
Yeah, we can. Thank you so much for joining. sorry about the difficulties.
My Zoom decided to update, and clearly it did not work.
Yeah, that's a pain. Sorry about that. Just wanted to introduce Kate. So thank you so much for joining. Please feel
free. You're just in time for my question.
Yes,
I am. Thank you for starting, Grace, and getting started without
Absolutely. Me. So I've sort of explained the coffee shop demo, and at this point, now that we've added in this event-driven system, a lot of people would say, okay, now that I've added this in, is my microservice non-blocking and highly responsive?
And we can say, yes, I'm using Kafka.
And then we say, no, because Kafka is a fantastic tool to use when you're building reactive systems, but it is not the be-all and end-all of reactive systems. You have to think on multiple different levels for your system to be truly reactive, from the data layer all the way up to the architecture layer. So although Kafka is a great tool, we need to think about using it in conjunction with other reactive tools to be able to make our system truly asynchronous, truly responsive, and truly non-blocking. So how do we make a highly responsive app? So we've got an example here with just 3 microservices. I'm sure many of your applications have many more microservices, but this is just an example. So here we're looking at, so as I said, Kafka is a really great tool, and it's great for making the data layer more reactive and more asynchronous and more sort of non-blocking. But as I said, we also need to think about the other layers of our applications. So we need to think about our actual microservices themselves. How do we make our individual microservices reactive? Well, we can use something called reactive programming to make them more reactive. And that includes things listed here like futures, reactive streams, and libraries. But we can't just think about the individual microservices, because most applications are made up of more than one microservice. So we have to think about the communication between these microservices. And that's where we think about sort of this reactive system, sort of architectural approach, where we're looking at, okay, how do my microservices communicate with each other? How is my system responding as a whole? So reactive programming, we're not going to focus too much on that, but just to give you a rough idea, reactive programming is more about the internal logic flow within a microservice. So it's all about driving the logic forward based on the availability of new information, rather than having it driven by a thread of execution. So that's reactive programming. And as I said, you can implement different techniques and patterns to be able to implement this within your microservices. So this includes things like futures. So just going over this quickly, a future is a promise to hold the result of some operation once that operation completes. I'm sure many of you have probably used them before. You've got things like reactive programming libraries. So there's RxJava, for example, or Small Mutiny. And there's also things like reactive streams. So that's essentially a programming concept for handling asynchronous data streams in a non-blocking manner while providing back pressure. So these are all patterns you can use within your microservices to make them more reactive and more responsive. So, as I said, the reactive programming is more on the microservice level. What about the system level, the whole application? So that's where concepts like reactive systems and the reactive manifesto come into play. So the reactive manifesto is essentially like a manifest document that was made in about 2013, and it is based on 4 cornerstones. So there's at the bottom, you've got message driven. So message driven is really highlighting the fact that in order to be a reactive system, in order to be highly responsive to your users, you have to have this basic layer of asynchronous data handling. And so that's where that message driven comes in, all about non-blocking message delivery to the components of your system. This, building on top of that, you can then have characteristics like elasticity and resiliency. Now, these are really important to reactive systems. Resiliency, especially. If you don't have a resilient application, you don't really have an application at all, because at any minute it could fail and go down. So it's really important that we build in resiliency into our applications for potential failures that could occur. We can't look forward to the future. We can't absolutely know of potential failures, but we have to be able to plan and implement and design our systems to be able to cope and deal with these failures that we might not be able to predict or sort of provide solutions for immediately. So it's really important we have that resiliency. Then you've got elasticity. So as I mentioned before, data is constant. The amount of traffic to our websites, the amount of data our applications are having to deal with fluctuates hugely depending on the day of the week, the season, the time. So it's really important that we're able to deal with these fluctuating loads to our system by being elastic, by being able to sort of re-architect our applications to put resources where they're most needed, to be able to be as cost efficient and as responsive as possible. And that's the last one, responsiveness. So by having this asynchronous backbone, this asynchronous message-driven backbone, and having elasticity and resiliency built into our systems, we can provide this highly responsive and reactive application that can respond to the events being given to it and provide the most up-to-date information for our clients and our users.
So how do we move towards these reactive and responsive architecture patterns? So there are a few different design patterns that are often used in these reactive systems to achieve these responsive results. We're not going to go through them all in detail. This could be a whole separate presentation, but I'm just going to give an overview of some of the ones that we've got here. So we've got CQRS, where you separate your write API from your read API so that you can make sure to optimize both the writes and the reads in your system. We have event sourcing, where all of the business objects in your architecture are represented as events. So if you wanted to represent an order, you would have an order being created and then updated and then deleted, rather than having a static order that you then edit the versions of. We then have the saga pattern. So this is a way of kind of getting what you would traditionally think of as a transaction, but you can't do that so well in a distributed system. So the way you set up a saga is you basically have a set of mini transactions. So for example, if I was going to place an order, I might say I'm going to put my order into a pending state, perform some other action like checking whether the stock is available. And then if I decide for some reason I can't fulfill this order, the stock isn't available, instead of saying, okay, well, I'm not going to commit that transaction because you don't have that same environment, what you do is you set up a backtracking action. So the forward action would be create a pending order, and then the backtracking would be, okay, I'm now going to put this as out of stock, and that's going to be the new status, and you can have other applications responding to that. So you have all of these events that are flowing through the system, but handling that transaction. And the idea is that eventually you're all consistent and you all have the same understanding of the system. And then finally, we have sharding. So running in a distributed system, you generally want to have each of the microservices owning their own data. And if you started with one large database, you might find that sharding and splitting the database down is the right thing to do so that each microservice can own its own data.
So we know that we can, we have all of these different patterns, and we've seen that event sourcing is part of those patterns. And obviously there's something called Kafka, and we've been looking at sort of how we can use Kafka in reactive systems. So how do we configure Kafka so that it's really built for these reactive systems? Because according to the Reactive Manifesto, we're looking for a message-driven asynchronous backbone. Now, I often think of Kafka as event-driven. So, Kate, how can we sort of configure, and how does Kafka fit into this message-driven asynchronous backbone?
That's definitely a really interesting question, and one that comes up a lot around Kafka, because like you say, a lot of people think of Kafka as being focused around events. Well, if we step back and look at what we have in the Reactive Manifesto, really, reactive systems rely on asynchronous message passing. So asynchronous being a really important term here, we're not waiting for a response, and we're passing messages around the system. One of the other things I find a lot talking about Kafka is you repeatedly get this question of messages versus events. So what is the difference there? Well, the way we would describe a message is it's an item of data that is being sent to a specific location, whereas an event is really a signal emitted by a component upon reaching a given state. But you can have a message that includes an event as part of its payload. So for the message, it's really thinking about that specific location and who the message is intended for, whereas an event is something you would normally think of as just a piece of information you're sending out to lots of people. And where Kafka started, it did favor more the event side. People were using it to be able to disconnect producers and consumers and send these events out across the system. But if you actually have a look at what's on the Kafka website and how they describe Kafka, you'll see that they aren't so specific about what's being passed around. So this is the definition that we have from the Kafka website. It's an open source distributed streaming platform, and there's 3 things they call out as being unique to Kafka and the kind of big reasons why people love Kafka. You can publish and subscribe to streams of records. You can store records in a durable way and process streams of records as they occur. And you'll notice here they haven't used the word message and they haven't used the word event, they just used the word record. So a record is the representation in Kafka of what you're passing around, but it's up to you to decide whether you're emitting events as records or whether you're actually sending messages as records. So Kafka can fit well in either scenario.
Cool. Okay, so we've seen that Kafka can provide us with this necessary asynchronous and non-blocking sort of message-driven backbone that we need in reactive applications. How can we enable resiliency in Kafka?
Well, the good news here is Kafka is well known for being resilient. It has resiliency built in. It's built as a distributed platform. So the fundamental level of Kafka, you have a cluster made up of different brokers, and normally you would have 3 brokers to start off with. And these you start off being distributed across different nodes. So if you're running on Kubernetes, you'd have your brokers on different nodes. And the way we send records around in Kafka, they are inside something called a topic. So a topic is a logical grouping of records. You get to decide which topics you have, how many, how few. And within that topic, it's also separated down into partitions and spread across different brokers. But the important thing is that for a specific topic and a specific partition within that topic, there is a leader. So that these brokers aren't all the same. They do have unique IDs, and a specific broker will be the leader for that topic and for that partition. This means that any clients that are trying to connect, they will talk directly to the leader. And if for some reason they connected initially to one of the followers, they'll get redirected to the leader. This means if for some reason the leader were to go down, we know that all of the clients have been connecting, but actually under the covers, Kafka has been copying all of these records onto the other brokers. So you can see here we've got topic A and partition 1 is copied across. And so all Kafka has to do is do a leader election. The Kafka clients will get rerouted, and that's already set up so it can do that. And they just start producing and consuming to the new leader. So Kafka really has been built with this resiliency in mind, and with the idea that you can have a broker go down and you can still carry on. And they actually go further than this. So when you're setting up your system, you would aim to have 3 at least brokers, because Kafka, some of the configuration options, you will need to bounce your brokers in order to have them make effect. They're moving away from that and gradually trying to make them more dynamic, but you should expect that it's perfectly reasonable to take down a broker, put it back, and Kafka will just carry on as normal. So Kafka is really designed with resiliency in mind. So stepping away from Kafka itself and looking at your applications, it's not enough to say, well, Kafka's resilient, so I'm fine. You do have to think about how your applications are going to communicate with Kafka and handle the records. So you can just do a simple fire and forget in Kafka. With your producers, you can just send the records, forget about them. If they get there, they do. If not, no worries. But that doesn't really build a very resilient system, because if something were to go wrong, then you're not handling any of those failures. So in Kafka, when we look at the kind of guarantees you can get end to end from a producer all the way through Kafka to the consumer, we think about having at least once and at most once. So you can configure your producers and Kafka together so that you can guarantee that the record will reach Kafka at least once. This does mean you have to deal with some duplicates. So when you're starting to build systems with Kafka and you want resiliency, you need to think about how you're going to handle duplicates in Kafka, or whether you're going to look at some way of having idempotent producers. The configuration that you have for Kafka in terms of producers, there's 2, there's acts and retries that you really need to think about for resiliency. Acts is short for acknowledgements. And basically what that means is when you're producing, you can choose how long or when, I guess, to wait for Kafka for that response. So you can either say, I don't want a response, that's fire and forget. Or you can say, I want the leader to tell me that it definitely received the record. Or you can actually say, I want the leader to have received the record and all of the followers to have received the records, and then I'll be happy. And if you set that up, then you'll find you have a lot of resiliency, because even if the leader goes down, then you'll know that the record already reached all of the brokers. Of course, you have to handle failure, so you do need to think about retries. Most of the Kafka clients have retries built in, but you will need to configure how many times you retry.
So we've talked about resilient producers. What about the consumer side? So as Kate mentioned, there's some configuration options you need to be thinking about when you're designing your systems to be reactive. In the consumer side, it's something called the offset or the commit offset. So an offset is essentially sort of the number of records along a topic that the consumer has reached. So it's used so that if a consumer goes down, they know where to pick up from again without duplicating any of the records. So in this case, on the diagram on the left, you can see that the offset goes from 0 to 5. And let's say, according to the blue line, we've only looked at offset 0. So if the broker was to go down, if the consumer was to go down, they would know when they come back up again to start at number 1 and not 0. So there are 2 options for committing your offset as a consumer. You can either do that manually or automatically. Now, it's probably easier if we go back to our coffee demo to see how this would actually play out and why this is an important configuration value when you're looking at resiliency in your consumer. So let's take a look at our barista. This time he has 3 records. So he's got 3 coffee orders to actually produce. Now let's look at it first with auto commit on. Now auto commit is based off essentially most of the time just a timer. So it's the amount of time since they last looked at that record. It will just commit the offset and move on to the next one. Now that can sometimes be a problem with resiliency. So let's take a look. So we're looking at the first record here, record 0. And with the barista starts off making his coffee. Now, obviously, after some arbitrary period of time, the auto commit decides, yep, we're going to commit that offset. Our consumer has read and processed that information. Unfortunately, the barista, during the process of making the coffee, drops the coffee. Now, that means we don't have the coffee anymore because it's on the floor. So our barista, this is essentially the same as saying our consumer or our consumer's gone down. So our consumer comes back up again, and our barista looks again at the topics and realizes his offset's already been committed for the first one for coffee. So he moves straight on to the cappuccino and then makes the latte. Now, what this means is that although it looks like our barista should have successfully completed all 3 of those, or successfully processed all 3 of those records, he's actually only successfully completed the cappuccino and the latte. We're missing the coffee. So this can be fixed by using manual commit. So with manual commit, you essentially decide when you commit the offset. So in this example, we're only going to commit the offset. So we're only going to say, yep, we finished processing that record when the coffee has actually been served to the customer, to prevent the possibility that our barista could drop the coffee or our consumer could go down before they finish those processes. So in this case, our barista makes the coffee, and the commit is only committed, the offset is only committed once that coffee has been served to the customer. So this way, our barista can ensure that the coffee gets to the client and we've successfully completed each coffee order in case it goes down. And if, for example, our barista did drop the coffee, he would know to start again at the coffee rather than starting at the cappuccino, because the offset hasn't been committed yet. So you can see this is a really important, another important configuration value you need to be considering when you're building your application. So we've looked at how Kafka itself is resilient. We've looked at how we can enable greater resiliency in our consumers and our producers. What about elasticity?
So when we talk about elasticity and Kafka, elasticity you would normally think of as being where something is being able to scale out really high and then scale back again. And you would think of that as being automatically. Now, in Kafka, you can scale out, but scaling back is a little more tricky because you've got this distributed system where you've got all the records on the new brokers potentially, and how do you then scale that back? So we'll talk about how you can scale and how Kafka is built for scaling applications in mind. So if we look back at how Kafka is configured, we have these topics and these partitions, and I sort of skated over the partitions before. For a particular topic and a particular partition, those are spread across the different brokers. So a topic is made up of records. Individual records are key value pairs, where your value is normally your message or your event. And the way a topic is set up, you will have lots of different partitions. These are spread out across all of the different brokers so that you don't have all of the traffic for a particular topic, if it's a busy topic, going to just one broker. So when we look at producers, this is pretty straightforward. When you send in your records, in the default case, if you haven't provided a key, it will just round robin between the different partitions. If you do configure a key, however, then Kafka allows you to configure a bit more closely which partitions you're producing to. So if you've set a specific key, it will always go to the same partition. The one thing to bear in mind is Kafka's ordering guarantees. So Kafka provides ordering within a specific partition. So if you're, for example, doing event sourcing and you have a set of records that are around the same object, so the same order, you would want to use the ID for that order as the key so that you know all of those are in the correct order when they're on that particular partition. So partitions is key to the scaling here. Let's have a look at consumers. The producers is fairly straightforward in Kafka. Consumers is a little bit more complicated, but Kafka has stuff set up so you can easily scale out and scale down your consumers. And we do that using consumer groups. So a consumer group in Kafka is just a consumer that when it has joined Kafka and declared that it's there, it gives a particular ID. And it's as simple as that. When they join, they just say, this is my ID, and every consumer with the same ID joins the same group. So we've got an example here. We've got consumer group A and consumer group B. There are 3 consumers in A and 2 in B, and we have 3 partitions on this topic. When the consumers start to receive records, what Kafka will do is it will make sure that between all of the consumers in a group, they will get all of the records. So in A, that means that, for example, one consumer will read partition 0, a second partition 1, and the third partition 2. Now in consumer group B, we only have 2 consumers. So one of the consumers has to read from 2 of the partitions. Kafka doesn't do any preference in terms of saying, well, there's more records on this one, so I'll give that to 1 and the others to 1. It is fairly random, so you do have to keep an eye on how well your consumers are coping if they're having to read multiple partitions. But the thing to bear in mind here is that you can achieve scale by basically creating new instances of your application and then joining with the same ID. But there are some limitations that you need to be aware of to do this effectively. So if I were to add another consumer to consumer group A, it wouldn't actually receive any records. And the reason for this is we want to keep that ordering in Kafka. So if more than one consumer receive the records, then you can't guarantee ordering anymore because different consumers are getting records from the same partition. So you can only scale out your consumers to then match the number of partitions. Otherwise, the extra ones just won't get any traffic. So this means when you're initially setting up, if you care about ordering and therefore don't want to be adding new partitions all the time, because that will change some of the ordering, you need to work out in advance what's the maximum you're going to want to scale your consumers out to, and make sure you have enough partitions to fulfill that. The great thing about Kafka is it is built with the idea that you can have a system that can handle a small number to a very great number of producers and consumers without having to make configuration changes. So it's really designed to be able to handle all these different loads, but you do have to be aware that you can't necessarily go adding brokers and then removing them again. That will cause you some difficulties and you'll have to do some manual intervention to move records around.
Cool. So we've seen how Kafka can provide us with this message-driven asynchronous backbone. It's got built-in resiliency, and we can add more resiliency to our consumers and our producers through configuration changes. And similarly, we can enable greater scalability and some instances of elasticity with Kafka by enabling these, by thinking about our configuration options carefully when we're designing and building our applications. So now that we've convinced you that Kafka is great for reactive systems, how do we get started with actually using Kafka and building a reactive and responsive Kafka application? So if you haven't used Kafka before, there's this great quick start guide that you can use, and you can just follow the first couple of steps to get Zookeeper and Kafka started. Now, you do still need Zookeeper. That will change in the future, and it will become essentially a topic within Kafka. But at the moment, for that metadata, you still need to start Zookeeper before you start Kafka. So if you use this quick start guide, you can get up and running within about 10 minutes with both Zookeeper and Kafka running. Now, what you get with Kafka sort of by default is these producer and consumer clients. Now, they are great when you're just starting off with Kafka, but when you're trying to build a reactive application, they don't necessarily provide the best clients available to enable resiliency and elasticity and responsiveness. So we suggest using things like reactive frameworks. Now, we're not expecting you to go and design and build your own reactive framework. There are tons of open source ones available already. And as I said, they are open source. They are free for you to use. So here are 4 of some of the most commonly used reactive frameworks for Kafka. So we have Reactive Kafka, we've got microprofile reactive messaging, Alpaca Kafka connector, and the Vertex Kafka client. And these help to simplify the Kafka APIs, help to provide things like back pressure, and help to provide important reactive concepts. So let's take a look at them in more detail. So you've got Reactive Kafka. So Reactive Kafka is essentially just, as most of these are just thin layers over the reactive streams, the Kafka client, essentially. And as I said, they help to hide the complexity of Kafka, and Reactive Kafka helps to add back pressure support too. This is based off sort of the Spring project. So if you're already using Spring in your applications, this might be a great framework for you to start looking at because it fits really nicely in with their sort of architecture style already. There's also microprofile reactive messaging. So if you haven't heard of microprofile, go and check that out. It's a specification. There's loads of great specifications out there, and it's made by multiple vendors, including IBM, Pyara, and a bunch of others. So it's a totally open sourced community project, all about adding sort of useful APIs and useful specifications to Java. So the reactive messaging API actually is a specific asynchronous messaging support, and it's based off the reactive streams implementation that microprofile implements. So there are several implementations of this, as of course microprofile is just a specification. So you will need to use some sort of implementation of it. So there's small I reactive messaging, you've got Open Liberty, Quarkus, or you can use WebSphere. So you can check any of those out. And the reactive messaging uses a method called sort of the channel framework. So if you're interested in learning more about that, that's a useful blog that we link to later on. So that's the microprofile spec. You've also got the Alpaca Kafka connector. So if you've used any of the sort of akka frameworks before, based on this concept of akka actors, then this is a useful framework to take a look at. It enables a connection between Kafka and akka streams, and again, provides that back pressure support and helps to hide that complexity within Kafka. And lastly, we've got Eclipse Vertex. This is a polyglot toolkit, and it's based on the reactor pattern. It also runs on the JVM, but as I said, it's polyglot, so you can use it in Groovy, Ruby, Java, Scala, and tons of other languages. This is, it actually runs on a distributed event bus, and it's single-threaded. So we chose to use Vertex in our own application based on multiple things, including the fact that it has this distributed event bus. It's single-threaded, so it really helped us when it came to building our application to ensure there weren't thread conflictions and to really simplify that logic. And it also, we chose it because it's also used in many open source projects that we've already used before, and for example, Kate's used, so things like Strimzy.
Yeah, so Grace mentioned we built a starter app. So this is actually an application that I created previously. I work on a product called Event Streams, which is a fully supported Kafka offering, and we wanted a really easy app to give to people to try out their event streams in Kafka and basically just work out that it is kind of working, but also to introduce some of the concepts of Kafka around offsets and partitions and what all of that means. So we originally built this application using the standard Java APIs that are part of Kafka, so those clients that Grace mentioned earlier. But as she said, we decided to rewrite it into Vertex just to kind of see what it would be like and see how much more reactive we can make it. And we were really pleased with how it came out. So we have, as the app, we have a Vertex-based app that is going to produce and consume from Kafka. It is just a demo app, so you wouldn't normally produce and then consume your own records back again, but for the purposes of the demo, that's what we wanted to do. And then we also wanted to have a UI where people could explore the records that have been sent and could look at some of the metadata that is in their records. So what partition is it on? What's the timestamp? That sort of thing. And we decided to use WebSockets to communicate between the UI and the backend because we wanted something where we could have this continuous sort of feed of updates as the records are consumed back again. So let's have a look at some of the things that we found when we moved across from the more traditional Kafka clients. So this is an example of the built-in Java Kafka client, Kafka producer, and the flow that you have to write in order to send records in. This is just the example from the docs. It's pretty straightforward. It's just going to loop round 100 times and send a record every time. When we switch across to the reactive framework, we can see that actually it's pretty similar. Grace, can you switch? Okay. And for producing, actually, because the way you would produce isn't a sort of event flow as much, it was fairly straightforward for us to set up this producing. But it was actually some of the pieces that Grace talked about around the single-threaded nature and the fact that we had a nice timer feature in Vertex that we could use. So we could actually, rather than having a loop like this in our Vertex app, we could kind of switch to having a timer that just fires a particular method on a timer and then have that do the producing. So the actual code of doing the produce line was pretty similar, but we definitely found some advantages of moving across to a more reactive framework. But it was the consumer side that we saw the most benefits in terms of switching to this more reactive style, and we felt that fit better. So if we look at what a consumer looks like normally, this is the example that we have again in the docs. So we've got a while true loop, and we're basically polling for new records. And then once we've got a set of records back, we then loop over every record, process them, and then do the commit, because of course we want to be resilient. So we want to process it and then do the commit manually. So this isn't the most reactive sort of flow. in a reactive system, you really want to have events coming through the system and then applications triggering off of those events. Whereas the loop we had before, we were having to handle, well, when are we going to keep looping and when are we going to stop? And we had a lot of problems with threading. So for the Vertex version, it actually flows a lot more like you would expect a reactive system, but it also fit much better with Kafka as an event-driven and message-driven system. So in the Vertex Kafka client, you configure it using this consumer.handler. And basically, Vertex will make sure that the consumer handler is called every time a new record comes in from Kafka. You can then set up a function to process the record, and then once you process the record, commit that offset. So it really meant that we could have a flow that felt much more reactive. We have written a full blog post on what we did here, and you can go check out the code. So do go have a look at the code. I don't think we're going to demo the application today, but the UI is on its way. It's not in the public repo yet, but we are working on it. But do have a go look at the code and see how little code we had to write in order to get this really nice system set up. And we've also written an article where we really went through all of the different areas where we found switching to a reactive system just fits so much nicer with Kafka.
So in summary, you can see, hopefully we've convinced you that building reactive can help you build more resilient, more scalable, elastic, and responsive applications that provide your users with a more responsive UI, essentially. And that Kafka can be a really useful tool when you're designing these reactive applications, but you need to think carefully when you're designing them about the configuration values and the configuration options that you've chosen. But the good news is you are not alone. And as we've shown you, there are loads of reactive frameworks you can use to help you along the way. And us, as well as many others, are producing documentation online to hopefully help you when you're using those reactive frameworks to make the best choices to make your applications as reactive as possible. If we haven't bored you enough already about reactive systems, we've actually written an ebook. It's only about 25 pages long. So if you'd like something sort of concise and all written down in one place to explain what reactive systems are, when it's good to use them, and the patterns used for them, check out this Reactive Systems Explained ebook. And if you're interested in getting hands-on with some reactive messaging scenarios and sort of getting your hands-on with some code with it, we have a microprofile reactive messaging guide on our Open Liberty site. So go and check that out so you can see how to implement reactive messaging in your own application.
So I mentioned earlier that I work on a product called IBM Event Streams. So if you are interested in a fully supported Kafka offering with some great UI design and things like geo-replication and connectors, then go have a look at Event Streams. And one of the best things about Kafka is it has such a big community. There are so many different projects that are really creating awesome stuff around Kafka. So we've put a whole bunch of links for you to go get started. We've got the Reactive Manifesto if you want to have a look at that. There's the Quick Start, but also Strimzy, which Grace mentioned earlier. So Strimzy is a fully open source operator for Kafka. So you should definitely check that out if you want to get started with Kafka on Kubernetes. And then we've got the links to all of those different reactive libraries, because you don't have to do it yourself. There are so many people doing awesome things with Kafka, so you should definitely check out those projects. Thank you so much for having us and for bearing with us with the technical difficulties at the beginning. And if anyone has any questions, we'd love to hear them, but you can also well.
Yeah, no worries, that was fine. I mean, it's you know, you're always going to have these kind of issues, right? So it's no worries about that. And yes, we have a couple of questions for you. Let's see if we're able to do them all. We have around 4 minutes left. So we have let me go quickly here for what we're having. So we have here like a quick comment from Jonathan Villa, our good friend from the Barcelona Jug. He mentions that Apache Camel is also an excellent client for Kafka and to start integration channels. Do you have any experience with the Camel as well? Do you recommend it?
I don't have any experience with it.
Yeah, I haven't tried it, but we'll have to check it out and potentially add it to this presentation for the future.
Yeah, Jonathan, send us the link.
Wonderful.
Yeah, there's so many different projects, it's hard to check them all out.
Yeah.
And we also have this question from João Rebelo. He's asking, is the Kafka leader reelection a blocking operation for the topic or partition? If so, how does that work in a reactive system?
So when the leader election happens, because one of your brokers has gone down, your applications will basically get sent a response from Kafka saying that you can't currently produce because you've got the wrong metadata, you've got the wrong leader. So in a reactive system, basically what you need to do is you need to configure your applications so that when they get those sort of messages back from Kafka, that it does retry and it should get sent through to the right leader as soon as it gets elected. So it does mean that you have to deal with some downtime in terms of Kafka saying, oh, you need to reconfigure and move to the right place. But as long as you set up your applications correctly, they should be able to retry pretty quickly and get back in again.
Cool.
So you have to deal, and I think if you've written your reactive apps properly, then they should be able to deal with things like networking problems and stuff like that anyway. So you shouldn't see much of a blip in terms of producing.
Wonderful. So I have here a couple of more questions. So another one from Nuno Caro. He's asking, as with any asynchronous piece of code, error handling is tricky. Which of one of the frameworks you mentioned you feel are better to handle them?
Oh, that's an interesting question. So I do like the Vertex one is the one I've looked at in the most detail in terms of the error handling, and they have some really nice functions that allow you to kind of capture the errors and track what's going on. I think it depends on which system you're running on. So my advice would probably just be to have a little look at the different ones and see what they offer you and see what seems to fit best. I don't know, Grace, if you've looked more into the microprofile one, but my expertise has more been around Vertex, and it has really good error handling.
Yeah, so I think microprofile also has some really good error handling. I've only actually written reactive apps with either Vertex or microprofile. I haven't personally used the Alpaca connector or the project reactor. But as Kate said, like, it's completely dependent on what system you're using, what architecture you currently have in place as to which one would suit your application better. So I'm going to take the consultancy answer and say it depends.
I think the other thing, though, to be aware of with Kafka is there are different types of errors that can come out of Kafka. There's retryable and non-retryable. So Kafka has a set of different error codes it can return, and it's worth having a look at whether the client handles it or whether you handle it in your apps in some way, looking at making sure you're going to retry on the retryable errors. So things like a leader election is a retryable error because basically you would expect the application to try again in a minute. Whereas, for example, an authorization error, if you're not authorized now, you're unlikely to be authorized in a minute. So that's a non-retryable one. So it's worth having a look at the Kafka response codes and seeing the difference there and making sure that your application does retry if it's a retryable error.
Wonderful. Okay, we are pretty much out of time. There's still one more question here. I'm going to ask him if you can give me a really, really quick answer for that. So the question is for Jose Rosa. He's asking, do you recommend only using reactive systems for new projects since the design and architecture phase is so important?
I would say no. I think that you can get the most benefit out of being able to convert as much as you can in terms of the communication and the architecture to be reactive, but you can also gain value from just doing reactive messaging, for example, or just implementing things like Kafka beneath it, and gradually working your way up, because we understand that not everyone is a greenfield project, and we have enterprise applications that are many years old, and it takes a lot of effort and energy and work to get it to be completely reactive. So I think there's value to be gained from even converting the smallest aspects to be reactive, so that they become non-blocking.
Okay, wonderful. So thank you so much, Kate and Grace, for being here with us today. If you have any questions, please feel free to follow Grace and Kate on Twitter. I'm pretty sure that they will be very happy to answer any questions that you might have.
Absolutely, yeah.
Right?
Yeah.
And again, thank you so much for joining us for Generation, and we hope that you can come to Portugal next year.
Look forward to it. Thanks
Thank you so much for having me.
Okay, bye-bye.
Thanks, bye.
Bye.